In this video segment, we're going to continue to develop some of the expressions for the rotational inertia of various objects about particular axes of rotation. So you've probably already seen where this equation comes from. I think in a previous lecture we also derived the formula for a thin rod rotated about its center, as well as the same thin rod rotated about its end. So in this video we want to express where this formula comes from. Okay, so the formula in particular says rotational inertia of a solid cylinder is equal to, what is it, 1/2 mr squared. Let's draw another picture of it. In the picture shown here in the summary, it shows it as a very long cylinder. Notice the axis, though. It's an axis that passes parallel to the length or the height of the cylinder and passes through the center. Well, what if we sliced it? What if we cut it so it was only this long? Just that shaded region, and the rest of it's gone. We'd still describe that as a solid cylinder, correct? Some people might call it a disc at that point, but there's really no distinction between those two shapes. So I'm not going to draw such a long or tall solid cylinder. I'll make it look more like a disc. The axis of rotation here is one that passes through the center and perpendicular to the plane of the disc. And we'll start with the same place we started our other derivations. The definition for rotational inertia is equal to the integral of r squared dm. And as always, we really need to picture what we mean by dm. So let's do that. Okay, so a few different ways we could break up the total mass, capital M, into a bunch of little bits of mass. We'll go like this. Here's maybe one way to do it. You might have the inclination to divide it up into a bunch of pieces like this. After all, I think we divided up a disk in this fashion before when coming up with this expression in general for rotational inertia. The problem is, if we do it that way, maybe the axis of rotation is our z-axis, and then we would have both an x and a y-axis, and each one of these bits of mass that we call dm would have some coordinate on both the x and y axes, and this would require us to do integration in 2 dimensions, and we want to limit our derivations here to calculus of a single variable. So I'm going to choose a different way in which I can fashion smaller bits of mass together in order to make one complete disk. Let me draw it one more time to show you what I'm talking about. Okay, so once again, here's our disk. Here's the axis of rotation. This time, I'm going to picture the little bits of mass as a bunch of rings. It kind of reminds me of those Russian nested dolls they call matryoshka. So if I had one cylindrical shell or ring like this, that would just represent a small bit of the total mass of the entire disk, and then I can nest that ring inside of a larger ring, and then that one still sits inside of yet another larger ring. And if I keep nesting these rings together like this, in the end I can build out a complete solid disk. So that's how I picture dm in this derivation, and it's very critical that you picture what dm represents in all of your derivations for rotational inertia. In fact, I'm going to take it a step further. I'm going to imagine, what if I took that red ring that I'm calling dm, and I'm going to make a dashed line, and imagine, what if I were to cut along that dashed line? Then I'd end up with a ring something like this. And then I can pull it out this way and pull it out this way and stretch it. Now if I were to do that, I would just be left with something like a thin sheet, right? Now if this disk has a height we call h, what are some other dimensions we can label? Well, instead of an x and y axis, I can just make an axis that works its way from the center outward in any direction, call that my radial axis. And then the distance right here, oh, let me make my pen a little larger. This distance would be capital R, a special value along that radial axis. Okay. So when I cut and unroll this DM, it has the exact same height, h. And what would this distance right here be? Okay, so capital R is a very specific value of radius that gets us from the center to the edge of our disk. But the DM is located at a fraction of that distance. So we need to label that as some smaller random value of lowercase r. So the ring goes around, this ring has a radius of little r, and it's a portion of the entire disk that has a radius capital R, and when I unroll it, the length is just the perimeter of this ring, so this would be 2 pi r. Oh, then what's this? Well, that just represents a very small thickness. We want to imagine that these rings are very thin so that their thickness t is much less than their radius r. But then again, the thickness is not exactly 0. In fact, the thickness takes up a small fraction of distance along the radial axis. And so instead of calling it t, it's just as well to say it's just a small bit of displacement along the radial axis. It has a thickness of dr. So there we go. We have a three-dimensional object with just a tiny bit of volume. The total volume of the entire disk would be what? The surface area times the height, and the surface area is pi capital R squared. So the volume is pi r squared h. That's the volume of the whole disk. So dV represents the volume of the ring that we're calling dm. And we can calculate that by multiplying length times width times height, or in other words, 2 pi r times dr times h, or 2 pi r h dr. Now, where are we going with all this? Well, we have a step 1 for a derivation, but somehow we're going to have to make a substitution for dm so that we can get this integral into a calculus of a single variable, and we want that single variable to be r. So we're going to recognize that the entire disk is made probably of just one continuous type of mass. In other words, it's not as if the density out toward the perimeter is any more or less than the density of the material near the interior. And so if the density is uniform, the amount of kilograms per cubic meter is consistent throughout. So that means the mass of the whole disk divided by its total volume would calculate out to be the same thing as the mass of the little ring divided by its fractional volume, or dm is capital M over capital V times dV. So there's the substitution we'll make. Finally, we get to step number 2. I is equal to the integral of r squared dm, where dm is m over v dv. And we'll continue to make substitutions. For example, we'll replace dv with 2 pi r h dr, and at some point we'll probably replace capital V with pi r squared h. Okay, so one substitution at a time. I equals capital, oops, a little messy, capital M over V times the integral of r squared 2 pi r h dr. 2 pi r h dr. All right. 2 pi and h are all constants. So now we have I equals 2 pi capital M h, 2 pi capital M h over v times the integral on r squared with an r gives us r cubed dr. Now what are our limits of integration? If I try to construct a solid disk out of several rings, then the smallest ring of all has a radius of practically 0, and then the outermost ring that builds up this entire shape, we're going from r equals 0 for the innermost ring to r equals capital R for the outermost ring. So we're integrating from 0 to capital R. Okay, step 5. I equals 2 pi mh over v, where v is pi r squared h. So pi capital R squared h times the integral of r cubed dr from 0 to r, but that's just going to give us 1/4 capital R to the 4th. Okay, so you might see what's the final result here. Pi cancels, h cancels, the 2 and the 1/4 give us a 1/2. Ooh, I think we're onto it here. I equals 1/2, and what are we left with? M over r squared times r to the 4th, the r squared and the r to the 4th cancel to give us r. There it is. Exactly what we thought we would get. I is equal to 1/2 mr squared. Okay, so it took a lot of visualization and a fair amount of work and substitution, but in the end, we got the result we expected. In our summary, the equation indeed says I is 1/2 mr squared for a solid cylinder rotated about an axis that passes through its center.